Welcome to the debate. When you look at it like a beautifully drawn map of a major city, there's something just deeply satisfying about the grid.
Oh, sure. The perfect right angles.
Right, exactly. You see the distinct neighborhoods, the sharply defined borders, the clean intersecting lines. It gives you this immediate sense of, well, total control. But anyone who has actually driven in a metropolis during rush hour,
It's a nightmare.
it is a complete nightmare because traffic, pollution, economic activity, they do not respect those neat little lines. They bleed across zones. They interact.
Yeah, I mean, the map is not the territory, right? It's a representation. And sometimes the cleaner and more organized that representation is, the more it obscures the very messy, deeply tangled reality of what's actually happening on the ground.
And that tension between the comforting clarity of a map and the chaotic complexity of reality is exactly what we are dissecting today. We're looking at the Ishikawa diagram.
Universally known on the shop floor as the Fishbone Diagram.
Yes, the fish. If you work in engineering, manufacturing, or frankly any kind of structured organizational management, you know this tool. It is the absolute backbone of root cause analysis. When a product defect happens, you draw the head of the fish as the problem, and you draw out these long bones, categorizing every potential input that could have led to that failure.
It is the ultimate corporate checklist.
Well, I argue it is much more than a checklist, which actually gets to the heart of our disagreement today. The central question we are exploring is this: does the Ishikawa diagram's rigid categorization of inputs provide the ultimate roadmap for finding a singular root cause?
Or does its compartmentalized structure artificially separate deeply interconnected technical processes, oversimplifying complex product defects?
Exactly. And my stance is that the diagram's systematic isolation of variables is an essential, scientifically rigorous process for continuous improvement.
Right. And I look at the exact same diagram and see a framework that fundamentally fails to account for the overlapping, systemic nature of modern technical failures.
All right, well, let's get right into the mechanics of why this tool is so ubiquitous. The sheer brilliance of the Ishikawa diagram lies in its relentless, structured categorization. Think about human psychology for a second.
Always a dangerous game in engineering.
Fair, but in technical and industrial environments, human beings are incredibly prone to confirmation bias. When a product defect occurs, say a batch of circuit boards comes off the line with short circuits, our immediate instinct is to blame the most visible factor.
The path of least resistance.
Right. We want to say the operator messed up or the soldering machine is broken. We jump to the first plausible conclusion, and the Ishikawa diagram exists to physically block that path of least resistance.
By forcing you to fill out the whole fish.
Yes. It forces teams to evaluate what we call the 6 M's and environment entirely independently. That is, man, machine, method, material, measurement, and environment. By forcing engineers and quality assurance teams to populate every single one of those branches before drawing a conclusion, it systematically eliminates diagnostic blind spots.
But the operative concept there is that it forces you to look at them entirely independently. And that is precisely where the framework fractures when applied to modern engineering.
I see why you think that, but let me give you a different perspective on that independence. The independence of those variables is the whole point. Look at how this works on a specific product defect scenario. The diagram ensures that highly technical, physically distinct factors are explicitly separated for triage.
How so?
Well, let's say one of the potential causes on the fishbone is uncalibrated micrometers, which falls under the measurement branch. That is a fundamentally different physical reality than an actuator malfunction, which falls under the machine branch.
Different physical realities, yes. I don't disagree that a wrench is different from a calibration weight.
And they require entirely different domain experts to solve them. If your micrometer is out of calibration, you need a metrology expert to recalibrate your instruments to a known standard. If your actuator is blown, you need a mechanical maintenance crew with wrenches and replacement parts.
Sure, the solutions are different.
This structured technical breakdown prevents teams from confusing symptoms. It narrows the focus so you can actually fix the physical reality of the problem. It isolates the variables.
I'm sorry, but
I just don't buy that. Let me tell you why. The problem is that physical reality on a manufacturing floor is rarely that neatly compartmentalized. The diagram creates this comforting illusion by displaying these possible causes in isolated silos.
They aren't silos, they're categories.
But when we look at technical process workflows, especially today, we have to recognize the intrinsic entanglement of these categories. Let's take one of the most common pairings on any fishbone diagram. You have incorrect procedures sitting neatly on the method branch and lack of training or human error sitting neatly on the man branch.
Right.
In what functional industrial environment are those actually independent variables?
They are independent in terms of how an organization remedies them. Rewriting a manual is an administrative engineering task. Retraining a floor worker is an operational task.
But treating them as distinct branches fails to capture the actual how and the why of the breakdown. Let's dig into the mechanics of that. If a standard operating procedure, a method, is poorly written, contradictory, or out of date, the operator is virtually guaranteed to commit what the company will classify as a human error.
Well, obviously, they interact.
But by forcing these interconnected realities onto separate bones of a fish, the diagram leads teams to chase isolated symptoms. It flattens a complex sequential chain reaction into separate, unconnected bones.
I think you're underestimating the intelligence of the engineers using the diagram. Nobody thinks the factory floor operates in a vacuum.
I'm not questioning the engineers. I'm critiquing the architecture of the tool they are forced to use. Let's look at how almost all modern, complex product defects actually happen. They don't happen because one variable fails in isolation. They happen as a cascading failure.
Okay, walk me through how the diagram fails a cascade.
Let's say your aerospace manufacturing floor experiences a subtle HVAC failure, leading to a localized high-temperature event near the CNC machines.
Okay, aerospace, high stakes. So high temperature goes on the environment branch.
Strictly on the environment branch, according to Ishikawa rules. But let's look at the physics. That ambient high temperature slightly alters the viscosity of the cutting fluid used in the machine. Because the fluid is thinner, the spindle vibrates out of tolerance, leading directly to an equipment malfunction.
Which goes on the machine branch.
Exactly. And because the machine is suddenly operating out of spec and making a strange noise, the operator attempts a manual override, panics, and makes a human error, the man branch.
Right, and if they fill out the diagram correctly, they capture all three of those vulnerabilities. They note the temperature, the spindle vibration, and the operator override.
They capture the vulnerabilities, but they flatten a sequential chain reaction into parallel, unconnected lines. It completely fails to visualize the causal relationship between the categories themselves.
That's an interesting point, though I would frame it differently. You're asking the diagram to do something it was never designed to do.
I'm asking it to find the root cause, which is its stated purpose.
But the fishbone is not a thermodynamic simulation of cascading physical variables. It is a diagnostic tool designed specifically to improve analysis and decision-making by acting as a collaborative visual anchor.
But if the visual anchor fundamentally misrepresents the physics of the failure, the collaboration is flawed from the start.
It's not misrepresenting reality. It's organizing human behavior so we can discover reality. When you have a cascading failure like the turbine blade scenario you just described, the hardest part isn't identifying the physics of the cutting fluid.
What is it then?
It's getting the right people in the room to actually communicate without getting defensive. Without the fishbone diagram, the floor operator blames the maintenance crew for poor machine upkeep, and quality assurance blames management for no standardized procedures. It's chaos.
So you're saying it's a psychological tool, not an engineering tool.
I'm saying it's both, because engineering relies on people. The Ishikawa framework forces everyone to put their hypotheses on a shared board, depersonalizing the conflict. The maintenance engineer takes ownership of the machine branch, the QA lead takes ownership of the method branch. It transforms a subjective finger-pointing exercise into an objective, structured investigation.
I come at it from a different way. I understand the value of depersonalizing conflict, but as an objective visual anchor, the diagram is actually highly deceptive because it lacks any mechanism for weighting the data.
Exact same visual weight. Someone suggests poor lighting under the environment branch. Someone else suggests catastrophic supplier metallurgy issues under the material branch.
Right, both go on the board.
Yeah, and the diagram draws both of those as identical lines pointing at the central spine. It doesn't actually identify the root cause. It merely crowdsources a list of hypotheses without providing the statistical or technical measurement systems needed to verify which branch is actually responsible for the defect.
Well, visual weight isn't the primary goal. It's about building a comprehensive inventory of possibilities. Teams are supposed to investigate those lines after they draw them.
Right, but the tool itself gives no guidance on how to prioritize that investigation. To actually find a root cause, engineers have to abandon the fishbone and use completely different tools, like Pareto analysis or regression testing.
Let's make sure we clarify those terms for the audience.
Sure. If you aren't using Pareto analysis, which is essentially the 80-20 rule, a way to mathematically figure out which 20% of the causes are creating 80% of your defects, you're just guessing.
Or you might use regression testing.
Exactly. A statistical way to see how changes in one variable, like temperature, mathematically correlate with changes in another, like spindle vibration. You need those mathematical models. The fishbone promises to find the root cause, but all it really does is outline a brainstorming session.
I'm not convinced by that line of reasoning, because you're critiquing the tool for not being a supercomputer. You're divorcing the diagram from how it is actually utilized by professionals on the ground.
Am I?
Yes. The tagline associated with the Ishikawa framework is that it is a simple diagram that leads to powerful solutions. The simplicity you are attacking is, in fact, its greatest feature.
A feature that produces a massive amount of noise.
A feature that produces accessibility. If you demand that a diagnostic tool visually represent complex statistical weighting, Pareto charts, and nonlinear causal loops, you create a tool so incredibly complicated that no one on the shop floor will actually use it.
That doesn't mean we should use a bad tool just because it's easy to draw.
It's not a bad tool. You can't ask a shift supervisor at 3 a.m. to run a regression analysis before they try to figure out why the packaging machine is jamming.
No, but you can ask them to use a tool that doesn't actively mislead them into thinking the packaging material and the packaging machine are entirely separate ecosystems.
It doesn't mislead. It democratizes the engineering process. By forcing technical teams to meticulously document every single variable, from work instructions to humidity to skills and training, it guarantees a comprehensive review.
A review of isolated parts.
Let's talk about how continuous improvement actually works in the real world. It doesn't happen because a genius systems engineer sits in a dark room and perfectly models a cascading failure on a whiteboard.
How does it happen then?
It happens because a cross-functional team systematically grinds through the variables. They check the laser calibration. They review the standard operating procedures line by line. They audit the titanium suppliers. The Fishbone Diagram is the engine of that systematic review. It directly enhances quality and continuous improvement because it demands that no stone is left unturned.
That's a compelling argument. But have you considered the psychology of that comprehensive review? Leaving no stone unturned can sometimes mean you're just moving rocks around while the house burns down.
Moving rocks around?
Yeah. Have you considered the cognitive bias of completionism?
Completionism. Elaborate on that.
It's the psychological dopamine hit a team gets when they fill out a complex chart. When a team populates all 6 branches of an Ishikawa diagram, they step back, look at the whiteboard, and feel a profound sense of accomplishment. They feel like they've solved the problem because they've mapped the data.
That just means they finished step 1.
But relying on a simplistic, linear diagram traps organizations in shallow problem solving because the satisfaction of filling out the chart replaces the hard work of understanding system dynamics. We are told to use the fishbone diagram to transform problems into opportunities.
Which it does by breaking paralysis.
But transforming a deep systemic defect into an opportunity requires much more than just displaying possible causes. It requires understanding the dynamic interactions between human motivation, age equipment, and measurement calibration nuances the Ishikawa diagram physically cannot visualize.
I mean, it gives you a clearly defined, categorized list of what to check.
It unties the knot, cuts it into pieces, and lays the strings out flat side by side. That gives teams a false sense of resolution when they check off individual boxes. We recalibrated the machine, or we gave the operator a pep talk, all without ever addressing the deeply coupled system dynamics that will inevitably cause the machine to fail again next week.
But untying the knot and laying the strings out flat is precisely how human beings process complex information. You can't fix a knot by staring at the tangled mass. You have to isolate and trace each individual string.
You have to look at how the strings cross each other.
Which brings us to the core of where we stand on this. When you step back and look at what we're actually arguing here, it comes down to how we approach overwhelming complexity. From my perspective, the Ishikawa diagram remains an unparalleled technical tool.
Even with its flaws?
Yes. By systematically organizing every possible input, from machinery maintenance and data calibration to raw materials and environment, it forces a level of analytical rigor that cuts through the chaos of a factory floor. It breaks down overwhelming, tangled problems into discrete, actionable components, directly reducing downtime and solving highly technical problems in a structured, democratic way.
And, my stance remains that while the Fishbone diagram is undoubtedly a useful starting point for a brainstorming session, modern technical defects are almost never isolated to a single bone on a diagram. We live in an era of incredibly complex, tightly coupled systems. True root causes live in the spaces, the feedback loops, and the interactions between those categories.
Right.
Relying too heavily on its compartmentalized structure risks treating the superficial symptoms while completely ignoring the underlying systemic disease.
I think where we absolutely converge today is recognizing that the true value of the Ishikawa diagram might not be in the final drawing itself, but in the social and analytical process it demands.
Oh, absolutely.
It undoubtedly sparks vital technical dialogue. It brings disparate teams together, the QA lead, the maintenance tech, the shift supervisor, and transforms unstructured, chaotic problems into organized, methodical investigations.
I can entirely agree with that. The act of gathering around a whiteboard, arguing about whether a subtle failure was truly a method issue or a machine issue. That friction is where the real diagnostic work happens. It's a tool for conversation and team alignment as much as it is a tool for engineering.
Precisely. There is always more to explore in how we structure our thinking and our troubleshooting. So, to our listeners, the next time you find yourself staring at a complex problem, whether it's a massive product defect on an assembly line, an organizational breakdown in your office, or just a personal project that's completely gone off the rails, look closely at the workflows and processes in your own field.
Think about the clean grid of the city map, and then look out the window at the reality of the traffic.
Exactly. Ask yourself if a cleanly categorized visual tool like the Ishikawa diagram provides the definitive answer you need to move forward, or if it merely scratches the surface of much deeper interconnected systemic issues. The map is in your hands. Thank you for joining us on The Debate.